Our next workshop is going to be from the folks at Veridise, looking at pushing the limits of automated detection of vulnerabilities in ZK circuits. We'll have John, Daniel, and Al presenting various parts of the presentation. And to start it off, I'll hand over to John.
Hello. It's been a bit of an adventure getting everything working here, and so luckily we've managed to record some things just in case this eventuality came. But yeah, so we're going to be talking about a couple of different things. We're going to be talking about some common bugs in ZK circuits, so I want to give a little bit of a disclaimer here. This is mainly going to focus on bugs within the circuit logic rather than in applications in general. So there's going to be certain types of bugs that we aren't going to cover, like application level bugs like not checking nullifiers in your application, or issues in hashing functions that can reduce the security guarantees that hashing functions can give you and stuff like that. Instead, we're just going to be looking at logical errors within bugs themselves, or within circuits themselves. Then we're going to be looking at some ways that Veridise has been developing in order to identify these bugs automatically. And so I'll be giving the first part of the talk, then Daniel will be starting to talk about static analysis and how to identify bugs in ZK circuits, and then finally Alp will be talking about how to use some graph theoretical notions in order to simplify the process of solving some of these problems. And so mainly I am just here to give the introduction, and so we're going to start with kind of the classical notion. What is a ZK circuit? I assume that most of the people in this audience are going to be aware of how a ZK circuit actually works, but just in case, I'll quickly go through this. So basically, the way a ZK circuit is going to work is you're going to have a circuit written in some language. That could be Circom, Halo 2, ArcWorks, Snarky 2, doesn't really matter the DSL or the language. But basically what you're going to get out of that is you're going to get a witness generator, which will generate your witness. That witness is going to include an assignment to all of your signals. And then you're also going to get a set of polynomial field equations. And so this could be in a couple of different formats depending on the proving system that you're using. So this could be R1CS, like a Planck table. Doesn't really matter. They're still equations that are going to have to be satisfied by your circuit. And then those equations are going to be used by the prover and the verifier in order to prove that, you have actually run this computation, and then verify that the computation has been run at the end. And so the important thing is, unlike in traditional programming languages, now your source code is going to contain two things. It's going to contain computation and constraints. And so traditionally in programming, you're just expressing a program. And so this notion is important because we're going to take advantage of it in several of the future parts of our work. So we are going to be showing most of our examples in Circom. The concepts that we're going to introduce here are not specific to Circom, but when it comes to showing circuits, it's just a little bit easier to show in Circom just because we can kind of directly show the computation without having to worry about whether or not you know Rust or a particular API. And so I'm going to quickly go over some of the Circom basics, and if you have any questions, let me know. Also, throughout the presentation, if you have questions, just raise your hand, shout them out, doesn't really matter. We're not going to be very formal about this. But basically, if we look at this Circom program, we can separate the components that we just talked about. So in the Circom component, you can take this circuit and you can separate it into the computation component. And so that's going to be this right here. You can tell what this is because in Circom, there's basically going to be three different types of operators in order to perform assignment and equality checking. So your first one, which is that arrow with the two dashes, is only going to express something in your computation. So you can see right here, that division ends up going in here. And then also the arrow with the double equal sign will also place something in your computation. However, it will also generate constraints, as we talked about previously. And so constraints in Circom are expressed using this triple equal sign. And so you can see here in our original circuit, you had that operation with the triple equals, which ends up being encoded in your computation, and also the arrow with the double equals also encodes a constraint. And so one thing that you'll notice is it's always safest to use the arrow with the double equals, but there are some times when you can't express something as a constraint, and so you might have to mix and match these operations. So specifically, just because of the form that equations are allowed to take in ZK circuits, some operations like division can't be expressed in your constraints, and so you have to use this single arrow rather than the double arrow. And so part of CIRCOM is going to require you to express things in either your computation or in constraints. And this is what we're going to be talking about quite a bit, because we have found that this leads to a lot of programming errors where people do not recognize what goes into either side of this problem. And that leads to programming bugs, because at some point you might have some computation that is not actually going to be checked in your constraints. So, putting this all together, I already kind of showed you how this works previously, but the computation component is going to encode your computation into a witness, and then those are going to be checked by your constraints, and this is why it's important to make sure that there is some sort of equivalence between the computation component and the constraint component. And so the goal is, in a lot of cases, not all cases, but you want to make sure that these two things are equivalent. And so I'm going to tell you what equivalence means, and that will be in a slide apparently. So first, let's talk about why we care about this. So ZK is still relatively new. And so traditionally what I would do is I would show you, oh, look at all of these bugs. We don't have a whole lot of that, but we still have had a couple of bugs. So specifically, Tornado Cache had an under-constrained circuit in their circuits, and they were actually able to find it before anyone else did. But the important thing here is, had an attacker found it, they were able to show that their vaults could have been drained by an attacker very slowly. And the important part is, because this is ZK, no one would have known about it. In addition to that, there have been a number of other ZK bugs that have been found before they were actually hacked. So Veridise actually found a bug in CircomLib, which corresponds to that first one. And then there have been a number of other disclosures that could have caused things like double spins in the past. So let me talk about equivalence really quick. So I mentioned that it's very important to make sure that your computation and constraints are equivalent. So let me define what that means exactly. So basically, I talked about the witness generator and your constraints previously. So your witness generator is basically a program. And the reason why that's important is because your witness generator is going to take in some inputs, and it's going to output some values. And so that value that it's going to output is essentially the outputs defined by your circuit, but also the entire witness that you're generating. Your constraints then are going to take in both your inputs and your outputs, and it's going to return, yes, this was verified, or no, it wasn't, basically. Or yes, this is able to be proven, or no, it's not. And so in a lot of cases, you're trying to, or the program that you're encoding is deterministic. And so basically what you want to ensure is that, because your program is deterministic, you want your constraints to be deterministic as well, in that your constraints are only going to accept a witness that was generated by your witness generator. If it's not, that means that there's some behavior that is outside the scope of your program, and that would still be accepted by your constraints. In a lot of cases, this is not intended by the developer of the circuit, and we'll show some cases where this can lead to some buggy behavior where someone can manipulate a witness in order to generate an attack. And so we'll be taking a look at that in a little bit. But essentially here, what I mean by equivalence is we want to ensure that given some program that takes in some input and generates an output, the constraints will only accept that input-output pair. And so that's what this is saying. So yeah. One thing that we'll be looking at throughout this talk and through the tools that we're going to look at, though, is how this can be violated and how we can use tools in order to look for these violations, because they often occur in kind of patterns, but also we can use very formal reasoning in order to identify these cases. So let's go ahead and first take a look at a taxonomy of bugs. So the transitions got screwed up here when exporting this to this laptop, but we'll just go past that. So we're going to just look at a couple of particular classes of bugs in this talk. And so specifically, we're going to look at under-constrained signals. So these are signals that can accept more than one possible value. Constraint computation discrepancies. So basically, that's looking at cases where your witness generator and your constraints differ. Unsafe component usage. So in this case, we're going to be looking at cases where someone declares a subcircuit and they don't use that quite correctly. And then finally, logical errors. And so this is going to correspond to cases where the user doesn't correctly understand like the semantics of the programming language that they're using, and they introduce something like field overflows and stuff like that. But we'll go through each of these in a little bit more specifics, and also I'll show a couple of examples, and they're pretty easy. I'll ask you guys if you can find the bugs. It'll be great. So first, let's talk about unconstrained signals. So basically, an unconstrained signal is going to correspond to one whose constraint is always true. And so what that means is it doesn't have any constraints on it. That signal is always going to be satisfied no matter what the value that it's assigned to is. So because it's accepting everything, this can obviously lead to programming errors if you intend for it to only accept a particular value. And so there are certain cases where this occurs. So this can occur where you have an output signal that's unconstrained. So that means that it doesn't matter the assignment of your input signals. Your output signal will accept everything. Or you can have unconstrained public signals where you take in a public signal, but you aren't actually constraining that public signal in any way. So we can take a look at an example here. And so I've already given you a hint about there's an unconstrained output signal. It's a fairly contrived example just to make it easy to look at. There's also apparently a typo that I didn't see, but let's ignore the sig A and assume that actually defined a signal. But looking at this, can anyone spot the programming error? I'll give you a couple of seconds. Anyone got it? It's right here. So basically what's happened in this case is you're just looping over the structure. You have defined that you have arrays of size n, but you aren't looping over the entire array. And so in this case, the n-1th entry is going to be completely unconstrained because someone didn't loop over to actually constrain n-1. So this is just a basic programming error where the problem that we have here is this particular output signal is completely unconstrained. Most likely the user wanted to constrain it to a plus b, but it basically means that out of n-1 will accept anything. The reason why this can be really bad is because, yes? So yeah, right. So this is constraining output of n-1 equal to a. The reason why that's bad is because basically what this should be checking is it should be checking to make sure that, and this is where the typo ends up coming in, I guess. Technically, a is overloaded in this case. That should be something like n. And so really what this is trying to constrain is that like out of n-1 should be equal to a of I plus b of I, or a of n-1 plus b of n-1, and that should be equal to n. And so really it's just because those constraints aren't included, it doesn't matter. You can pass in n for the output signal, but it's not actually correlating that to a and b, which should be the intention here, because you should have a correlation between a of I, and b of I. Like I said, I don't know when that error got introduced, but either way. So basically, you have a logical error because out of n-1 is unconstrained, and so the relationship that you're expecting to hold here might not necessarily hold. Yeah, so the reason why this is important is because values that you expect might, or the relationship that you expect might hold won't. And then on top of that, if you have an unconstrained value like this, through traditional testing, you might not catch it because essentially you would have to start manipulating the witness generator in order to actually, or the witness to reveal cases where a value is unconstrained. Okay, so now we're going to look at some examples where subcircuits are incorrect. And so basically what we found is in a lot of cases, subcircuits often assume that constraints are going to be placed on either the inputs or the outputs, but this does not always occur. And so this corresponds to cases where subcircuits do not follow certain assumptions. So if you're familiar with circumlib, for example, there are assumptions that are placed on certain circuits. So for example, less than and greater than assume that you've performed num to bits to check that the inputs are of a particular size, so it can do the comparison efficiently. And so this is going to correspond to cases where those subcircuits aren't used correctly. And so if we look at an example of this, this one does not have a bug, so apologies for that. But can anyone spot where the bug might be here? I'll give you a couple more seconds. All right, does anyone think that they have it? All right, I'm gonna show it. So basically, you have a missing constraint. And in particular, you're performing this comparison, this less than comparison. But the important thing is, in circum, or in similar languages, it doesn't actually assert anything about whether A is less than B. Instead, it's requiring that the user actually insert a constraint to say that this relationship is going to hold. And so essentially what's happening here is someone is performing this comparison, but they're never asserting that A has to be less, or BAL has to be less than amount. Instead, that is completely undefined, so it's not actually enforcing the relationship that the user expects. And so because of this, what happens is, given the context that this is called withdraw, essentially an attacker would be able to withdraw more funds than they should be allowed to because it's not actually enforcing this less than comparison. Anyone have any questions about this? Okay. Okay, so then if we move on, this is probably the most interesting case that we're going to be looking at, in my opinion. And so this is going to be looking for cases where you have discrepancies between your constraints and your computation. And so basically what happens is, as I talked about previously, not all computation can be directly encoded as constraints. This is because constraints have to have a particular form, and this is enforced by a lot of different ZK DSLs. And so this is going to correspond to constraints that don't correctly encode the computation semantics. And so basically what we're going to look at is one particular case called divide by zero. And so the title kind of spoils it. So what do you guys think is wrong in this case? I'll just move on because people are laughing. Basically what happens is you have a division. The important thing here is that we all know that you cannot actually divide by zero, which means that in your computation there's this implicit constraint that you have that B cannot be zero. But because you cannot directly encode division as an actual constraint, you have to essentially construct that constraint in a different way. So a lot of people construct it like this, where, you know, basically they move the division and end up performing a multiplication by the other side. The thing that people don't end up checking, though, that we found, is they often don't check the case where B is not equal to zero. Now this becomes really important because in a lot of cases, they assume that B cannot be zero, but this is not checked anywhere in your constraint, so someone can manipulate your witness, and it essentially causes an unconstrained signal. And what I mean by that is if we assign B equal to zero, then that means that, you know, A would also have to be zero, but they can set out to any value that they want. So in the case where B and A are equal to 0, out is completely unconstrained, and it can be set to any value that the attacker desires. So depending on how someone is using this circuit, this can allow them to essentially manipulate this computation. And again, performing end-to-end testing would not end up catching this case because when you test, you're going to be using this witness generator, and this witness generator will never generate that type of witness. And so this is why it's important to start looking at other tools that we'll be talking about in a couple of minutes now. So the last case that I'm going to talk about is logic errors. And so again, the bugs that we're going to be looking at here aren't necessarily comprehensive. There are definitely other cases that you'll see in other languages, and I believe there's another talk about ZK bugs that I think will be more comprehensive in the main talk. But out of time constraints, we're just going to talk about these. So basically, what I'm going to define a logic error as is a programming error caused by someone misunderstanding the semantics of an operation. So whereas, with computation constraint bugs, it's caused by someone not encoding the semantics of a particular operation as constraints directly, in this case, someone might not understand the actual semantics of an operation, no matter where it is included. So if we look at this particular case, the important thing here is we have a transfer. It's basically just going to define, it's going to take funds away from one person and give them to another person. Contrived example, but importantly, a lot of people who are programming in languages like Solidity are now expecting that there's going to be automatic overflow checking or underflow checking. In a lot of ZK languages, you get none of that. And so that means that in this case, because you're not actually checking the relationship between the balance and the amount, you can actually end up having an overflow right there or an underflow right there. And so this can be particularly bad. We've seen a lot of cases like this in old Solidity code where an underflow can give someone an arbitrarily large balance because an attacker takes advantage of this. And so here, the important thing is this output value can become arbitrarily large. And this is actually, all of the bugs that I've talked about so far are bugs that we found during the course of our audits. And they are very common bugs that we found during the course of our audits, which is why they're really important. And so, as I talked about previously, end-to-end testing is not going to end up catching a lot of these bugs. Some of them can be caught using end-to-end testing, but when you start looking at things like under-constrained values, you're going to need to start looking at different methodologies of identifying these bugs. And so in order to do that, Veridise has been working on creating a number of different tools, and we're basically going to focus on two of them today, namely static analysis and formal verification. So first we're going to talk about how you can statically identify some of these bugs using static analysis, and then we'll talk about how you can actually formally verify that a circuit is constrained and how to actually make that scalable. So I'm going to hand it over to Daniel, who's going to be talking about static analysis.
Okay, so before I move on to static analysis, any questions so far about ZIRCOM in general? Okay, so since John already gave a really nice introduction to ZIRCOM, I had this here, this motivating example. I explain a little bit the components of ZIRCOM, but you already know that. So the idea here of this algorithm is we take two inputs that are supposed to be bits, and we just add them. And since it's bits addition, we get carries for inputs and outputs, usual stuff. And we make sure that the outputs are going to be Boolean with these constraints here. Because if you do the math for this for any other value that is not a 0 or a 1, that will not pass. So that's how you make sure. But here there is also a problem, which is since we are using the singular row, and we are only checking if the outputs are bits. We are not constraining much more than that. So the inputs are not constrained, and also, as you will see on the examples when I show you the tool, the outputs are also considered not constrained because they do not depend on the inputs. So, little bit of what is static analysis. We take a source code. zkVanguard right now only supports circom, but the idea is we have a bunch of detectors, we call them. It's just checking for some patterns or structures of the code or heuristics in general. One is the unconstrained output I just mentioned, but we have a bunch more. I will talk about a few of them. And then we just get a report saying like, hey, we detected this common pitfall that you may fall into. And static analysis, for those that don't really know what's going on here, we get the witness that previously we defined as P, and then we get the inputs. So we kind of plot this map of inputs and outputs. That's our programs, no? So we can just go sequentially and try every X, and we get every P of X, and then we get the results, and we know if they are good or bad. But that's very expensive or sometimes impossible directly. So we try to transform the program into a structure that we can understand. And the most common and classic technique was to take the program, transform it into a set of equations, and we just solve them. Something similar to what we do with R1CS. Once we get the results for the equation, we just check if the values make sense or not, and they are an issue or not. Other techniques, take for example, if we have an addition of integers, that could be 0, it could be a positive integer or just a negative integer. So we transform all those values into minus, 0, and plus, and then we define this special sum operation. Well, multiplication would be easier to think about, like this multiplication where minus times plus is minus, because that's how multiplication works. So we don't really know what number is, but we know it's a negative number, for example. And then, in other cases, we just take the shape of the program and we transform it into another one that is easier to reason about. And this is what we do with Vanguard, because in the particular case of Circom and the other ZK languages, you don't only have P, which is what you have in traditional programs, you also have the constraints. So we need to mix everything together. So we can reason about both of them at the same time. So, yeah. The main problem with static analysis, and that's why in the slide before we said it has false positives, is we paint like a very broad picture of what the program is doing. So we'll be missing cases, which will be false negatives because we are not seeing those. And since we have this very big circle, we may say that something here is actually true when it's not, because it's not one of the dots I painted before, right? So that's an inherent limitation of static analysis, because we are abstracting so far away, we lose the details. But it's okay. It's a trade-off that we are willing to do. So how we understand the programs in Vanguard? We have the inputs, and that should be, yeah. The inputs and the outputs. The outputs are slightly darker colored, and then we define the assignments, the single arrow, as these thick lines. So we say that I write something in O, we don't really care, and then the constraint is defined with the dotted arrow, so I constrain somehow O. They're related in a constraint. So we build a graph of all the inputs and outputs, and then we can detect some things following patterns in that graph. So, coming back to the example, we have the 3 inputs and the 2 outputs. So we just paint those. Then, there was supposed to be animations, but we lost those. Okay. So, we have the single arrows that take as inputs the 3 signals, and they write to each one of those outputs. So we get that bipartite graph. And then the constraints, since they are only related to themselves, we just paint those arrows there. So we said before, okay, the inputs and the outputs are not constrained between themselves, as we said before, but here it's like very clear to see, because there are no relationships between the inputs and the outputs using the dotted lines, right? So we can see here very easily that these signals, the input signals are unconstrained because there are no dotted lines pointed to outputs, and vice versa. Okay. And yeah, I forgot about this part. So, okay. regarding my turn of thought. So with this circuit, and since this is unconstrained, we can have this assignment, for example, this witness, where we try to sum 1 plus 0 is equal to 1. Good enough. But since we are only checking if the outputs are bits, we can do this, where we only change the carry output to be a 1. So we are trying to claim that we somehow did 1 plus 0 equals 3. And the constraint system will say OK, because that they are just checking that they're bits, but the math doesn't really add up. So why not just use the double arrow? We already talked a little bit about this. In this case, well, for the carry, we have an addition here. That's easy to spot. But this is a modulo operation, so you know it's also an addition, but we just take the remainder. So the constraints need to be quadratic, and the compiler actually detects all this. So you can see, like, OK, the double arrow is not allowed, so you cannot compile this. Like we already said, then you need to write things with this structure, which lead to programming errors that I made while making the slides. I actually made this one by mistake. This was not on purpose, and it was quite funny to notice. So yeah, since because of the limitations of Circon, we tend to make these mistakes. So more patterns that we can detect. In the case of unconstrained outputs, we just check the opposite relationship. Are there outputs not connected by a dotted line to the inputs? The unconstrained input I just said, and what we call a data flow constraint discrepancy. This comes from the fact that we consider the thick lines as data flows from the inputs to that particular output, and there is like they do not match between the dotted lines and the. Sorry, it's been a while since I gave a talk, so I'm a little bit rusty. So there is a discrepancy between the dotted lines and the thick lines. That's what I wanted to say. So let's take a look at some examples at the shape of the graph, and let's see if we can see the pattern. How can we detect all this? So let's look at the example we already knew of less than, and we are missing the constraint to the output. So we start working on this, and we take the inputs. Then we have the subcomponent, so we are going to define it with that. I created the box just to clarify what signals belong to what component. But in the end, it's just like the same graph mixed together. We have, since this is a double arrow, we have both a thick and a dot line. And internally, we know they have that shape. So how we detect in this, using this graph, thinking like the algorithm in Vanguard, how we will detect that we are using this component in a wrong way. Okay, so the idea will be, we know that subcomponent has an output, but nowhere in the graph that output is constrained to something in the main circuit. So we are missing that chunk there to some probably a signal that should be constraining. So if we are missing that chunk, we consider that we are not using the subcomponent. Okay, clear so far? Okay. Now, this will be what we call a non-deterministic circuit. We have here x2 is odd or even, then we assign 0 or 1, and we use that 0 or 1 as the index for x1. So depending on the value of x2, we will use either signal. So that's non-deterministic. And I got away with that because I use a single arrow, so Circle will not complain about that. And then I just constrain that for good measure. So we get that graph. And then again, the question is, okay, how can we build an algorithm over the graph that detects that issue? Here, obviously we can't, because following the rules we had so far, there is no way to know. X2 is just there, chilling, doesn't really connect to anything. So we just create, I forgot about the label. we create a new node, which represents a conditional operation, like the usual diamond symbol. And OK, with those rules now, the detection is obvious, right? We just check if any signal points to the conditional part of the fun statement, and if so, then we have that. This one in particular is not a bug, but it's considered a smell because it could lead to problems. It's not a problem on its own. And I mean, this is a very weird example. Like, you don't really do this in real life, but sometimes you do something that counts as, detecting it early is super easy, and pays off. So let's go back to the division by 0. Easy stuff again, right? We just know that x2 should be, well, it's problematic because it's there. So we then again have the graph, and then again we encounter the same issue. We don't have enough information there, right? So here I have a really nice animation, but with everything moved and was clear, but OK, whatever. So we create a new node that represents the operation. And then again, easy stuff, right? Like how will we detect here? We just have the node there connected to a division operation. This is simplified, though usually has to be the divisor. I was denominator. I mean, I learned math in Spanish, not in English, so some concepts don't really translate well. But yeah, that part of the division, the one on the right. So, OK, easy stuff, but with just that pattern, if we actually check if the value is 0, are we going to still complain or not? So consider this example now. Now we have the subcomponent that checks this is 0, this is from circle leaves, so standard stuff. And we just check, and we make sure that x2 is 0. Otherwise, this program will crash. The witness node will not complete. So we create this graph. So far, so good, no? OK. So an animation missing there somehow. Is this case vulnerable? Is this an issue? No, right? OK. So we will follow the previous algorithm. What will the algorithm say? Is this vulnerable? Yes, because it's just checking if there exists an edge between an input signal and the denominator of a division. So if we don't consider the value of x2 following this, we will have the report, which is a false positive because this is actually not vulnerable, which is kind of the main limitation of static analysis. Like, depending on how you abstract, on how you represent things, you may run into problems and detections that do not make sense, or you may miss cases. So if we wanted to make this right, we will need to consider the value of the output of this is 0, and make sure that all the values that are available is the ones that make this true, which will be 0. And then we follow the same procedure in the internals of is 0. Then we will conclude that it needs to be 0 in order for this to be true. So we can rule out 0. No, sorry, the opposite. If this is 0, then x2 cannot be 0. Always mix the two. So we can rule out from the set of possible values that x2 is going to be 0. So then we check if the value cannot be 0, then that division is safe. But then we already introduced another static analysis technique. So we are mixing things together. We need to improve and make it more complicated. So yeah, it really depends on what you do. You may have false positives, and no technique is perfect. As far as I know, there are no silver bullets on the static analysis. So that's why we also make other stuff to help with these more complicated cases, which now Alp will explain about. Because okay, that's all my slides.
Thank you very much. So I'll just talk a bit about how to use formal methods, basically, and SMT solvers in the detection of bugs in ZK circuits. And today I'll just concentrate on under-constrained circuits, but of course, by modifying things, you can also apply the same kind of reasoning for detecting other kind of bugs. So, I mean, John talked a bit about what under-constrained circuits are. So if you have a ZK application, you usually have like a computation part where you have input X giving you an output Y. That would be kind of your witness generation. And on the other hand, you have the set of constraints, and you want that the set of constraints really captures the computation. So you want to have this equivalence between the two. Yeah, and the set of constraints will be in general given by some polynomial equation, and your circuit will be unconstrained in general, if f of x is equal to y, then you want that the constraint should be satisfied. But if you have also, so if there exists x and y such that f of x is not equal to y, so this doesn't correspond to an input-output, but still the constraint is satisfied, that would be kind of a problematic case, showing that your constraints do not really capture the computation that you want to create a proof about, right? So this equivalence will be important. So basically you want that f of x is equal to y if and only if x and y really satisfy all the constraints, right? But in practice, this doesn't happen always, and that's a source of a bug. And the aim is to kind of discover or to reveal those. Yeah? And Daniel talked about static analysis, where you apply some predefined rules to quickly detect whether these circuits are properly constrained. I'll talk about how to use SMT reasoning to do that. So basically what you do is you express this under-constraintness property just as a formula in first-order logic. Yeah? So you say the circuit is under constraint if there exists x and outputs y1 and y2, such that y1 is different from y2, but both the pair x, y1 satisfy the circuits and x, y2 satisfy the circuit, right? I mean, f of x can be only y1 or y2 if it's a deterministic computation. So if you have two separate outputs that could really satisfy the circuit for the same input, then there's a high chance that there's something fishy there. Yeah? So you have this logical formula, and you want to see whether this can be satisfied. Yeah? So if this is satisfiable, then you are kind of, you should be watching out that, because there is high probability that there's something wrong there. Yeah, and the moment you talk about satisfiability, of course, you think of these SAT solvers, SAT solvers, but these were, they're very useful, but they're more for a Boolean satisfiability problem. Yeah, so you just have propositional logic, and you have like some formula, and then you want to see whether there is some interpretation. So if there's some assignment of truth values to your variables such that it evaluates to true at the end, right? But in our case, our problem is a bit more complicated, because we have like multiplication of elements, we have field elements, finite field elements, we have variables, and so on. Yeah? So it's not just a simple Boolean satisfiability problem. So this is what one usually studies under the umbrella of satisfiability modulo theories, which basically generalize SAT to more complex formulas. Yeah? So you include an additional theory. So this theory could be depending on what you are doing. It could be the theory of integers, of real numbers. In most cases for us, it will be the theory of finite fields, but you can have lists, arrays, and many other structures. Yeah? So, and what the SMT solver does is it takes a first-order logic formula over a given background theory T. So you have this theory of, let's say, integers together with all the axioms of the integers and some statements, some logical expression that expresses something about the integers, right? And what the SMT solver does is it should either say this is not satisfiable, or it will conclude that it is satisfiable and possibly give you a model. It should give you a satisfying assignment in the end, right? And just to give you a flavor of what kind of theories one could look at, for instance, just the theory of integers, where you only include addition. So this would be just the linear integer arithmetic or Pressburg arithmetic, and this is a complete and decidable theory. So you have algorithms that can kind of reason about this, but it is not too expressive because you cannot talk about divisibility, prime numbers, or nonlinear equations, and so on. And as you all probably know, if you include also multiplication, so if you go to a nonlinear integer arithmetic, the usual Peano arithmetic, then you get the incomplete and undecidable theory. Or maybe just to give you an example that's more easy to visualize, if you work over the real numbers, if you just have linear real arithmetic, then you would be kind of reasoning with methods like the simplex method and so on. Or if you include nonlinear real arithmetic, which is kind of very interestingly decidable by itself, so you can really find algorithms to solve whether a formula in this theory is satisfiable or not, using quantifier elimination. And I mean, this theory goes all the way back to Tarski, and currently the fastest algorithms are like the CAD algorithms to deal with them. And of course, the list of theories that you could be looking at, there are plenty of them. These are just the list of theories that are that you can use in this solver CVC5. Yeah? So I'll just go a bit quick. So just to give an example, for instance, over the reals, you could have such a system that you want to be satisfied, right? You're looking for real numbers x and y such that those three conditions are satisfied. How do you feed it into a SMT solver? It just has a certain syntax. You feed it in and you run it. Since it is decidable, if you're lucky, in a finite amount of time, you will just get a result which says, yes, it is satisfiable, and this is a model. Yeah. So, and that would correspond to kind of you're looking for a point inside the circle on the blue curves, such that the x and the y coordinate are distinct, and then this one -2 and comma, oops, there's a mistake. There's, yeah, -2 comma -1/2 will be a satisfying assignment. And the nice thing about quantifier elimination is it's so powerful that you can even give a formula that has quantifiers in it, right? You can give a formula saying there exists an x such that x squared is equal to a, and you're looking for an a that satisfies this. Yeah? So the only free variable here is a. Can I find a satisfying assignment? Means can I find an a such that there exists an x such that x squared is equal to a? So if you run the quantifier elimination, it will just eliminate your quantifier and will reduce it to a formula which is quantifier free. It will say that a should be either equal to 0 or a should be less than or equal to 0. And you can play around. It's a lot of fun. You can look at degree 2 polynomial equations, right? And you can ask, oh, I want to have a, b, c such that there exists an x such that this equation holds. So you're asking, when does a degree 2 polynomial has a root? And then you eliminate the quantifier, and it reduces to an equation. I mean, if you see what this means, it just says, okay, the discriminant should be non-negative, basically, what we know from high school. Yeah, so it's a very powerful tool. Just to show you how nice SMT solvers are, for us, it will be more interesting to look at the theory of finite fields, not the theory of real numbers, because our constraints in the end will be just equations over a finite field, polynomial equations. So there is a public fork of the CVC5 solver developed by Özdemir, Kramer, Tinelli, and Barrett, which kind of includes this theory of finite fields in it. And it's basically based on Groebner basis implemented in a computer algebra system called Cocoa. And that you can really try to use. You can use that SMT solver to do like some kind of more formal verification. So there were two strategies, as I mentioned. There's static analysis that Daniel talked about, which is scalable but has many false positives. And then we have this method also employing SMT solvers, which is more precise, but it does not scale. And the reason why it does not scale is basically if you trace where the bottleneck is, it's at the end you have to kind of solve polynomial equations over finite fields, which reduces to some Groebner basis computation or solving polynomial equations, which is an inherently difficult problem. Yeah. And at Veridise, we have developed a tool called Picus, which kind of tries to combine the nice things of those two worlds. I'll just go very quickly over it. It just takes in these polynomial equations, and it tries to reason. It tries to determine whether the output is uniquely determined, right? So if the output is unique, you just get a positive result saying yes, the circuit is properly constrained, or if sometimes you can prove that it is not properly constrained, and there are cases where you cannot really get a response, and the reason why you cannot get a response is it times out, basically. Yeah. But you do combine the kind of strengths of static analysis and SMT solvers, which is, on one hand, it is fast, but imprecise. The static analysis is fast but imprecise, and SMT solvers are precise but slow. And this way, you manage to get something that is both fast and precise in some sense. Yeah. And how this works is basically, I won't go into the details, but it's kind of an interactive loop between two engines, one doing the static analysis phase and one doing the SMT phase, and both can get stuck, and then they feed each other, they pass information from one to the other, and whenever one gets stuck, it passes it on to the other, and through this communication, in the end, you can conclude in most cases that something is under constraint, which without having this engagement between the two would not have been possible. But eventually, you get quite some speed up, but eventually this is also reaching its limits, because the SMT solver in the end you take weight off from the SMT solver, but still it has to do some heavy computation. And the reason is that the Groebner basis computations is, in fact, a doubly exponential problem. Yeah? So that's the main bottleneck. And then the problem is, okay, what to do with it? Yeah? So one thing you could do is you could say, okay, I'll wait until people working on commutative algebra or computer algebra systems improve their methods for solving polynomial equations. But if you take into account that that field has been around for several decades, there won't be a major breakthrough, most likely, in the next few years, right? But what you can do is you can exploit the fact that the system of polynomial equations that you would be working with in ZK applications have a very particular form. Yeah? So they're all quadratic equations. They are very sparse by definition and so on. So, you can try to use that structure and exploit it to really speed up things. And the idea to kind of exploit the structure, to understand the structure of those polynomial systems, is to just attach to the polynomial system of equations a graph. So it's a graph where for each variable that appears in your system, you have a vertex, and you draw an edge between two vertices exactly when they appear in an equation together. Yeah? So for instance, for a circuit, like for the FP multiply circuit, you get a graph that looks like this, right? It looks quite complicated, so it has 377 variables and 392 equations. If you forget about multiple edges, it looks a bit better. So, here already, you see that there are some clusters of variables that communicate a lot with each other, right? But the variable here would not really care too much about the value of a variable maybe in the other cluster. Yeah? So they only speak to each other through these edges over here, right? So kind of you try to divide your problem into smaller problems using this graph theoretic approach. Another thing that you can get out of it is, this connectivity is an important point, right? Variables here, they would kind of, with the central component, only talk over this edge over here. And then you might wonder, what are those weird-looking arms? Let me try to understand the structure of my constraints by understanding what those arms correspond to, right? And when you do that, you see basically that what those arms correspond to, they just correspond to certain bit sums, right? So if you take one of those arms, you will have one vertex where it connects to the main body, right? That would correspond to one variable, and then you'll have several other variables. And then if you look at the corresponding equations that form this arm, you will see that it just corresponds to saying X has a binary expansion, so I can write it as a sum of bits, right, by multiplying with consecutive powers of 2, and each of these b0 up to bk are bits, right? So what a whole arm like this would be saying is that this variable corresponding to the part where the arm connects to the body is constrained to a certain interval, right? So if you want to express this range analysis using polynomial equations, this is how it would look like. Yeah? But then the problem is this does not translate well into algebra. Yeah? If you would convert this problem, even if you have a small, like if you have just 14 bits, a very small number, if you want to translate this into algebra, into a polynomial equation, what you would be doing is basically you would use Groebner basis to eliminate those bits over there and see which equation the x itself has to satisfy, right? Because that's what you care about in the end. So the whole arm is just there to express what you know about the x. And then if you take such a range constraint, if you translate it into algebra, it would just say that x can take a value between 0 and 16,383. But then this corresponds to a polynomial which has a very high degree. And if you look at the coefficients, they are huge. Right? I mean, there are coefficients that are, the constant coefficient is just the product of all numbers up to 16,383. So it's kind of a 61,000, almost 62,000 digit number. Yeah? And that's why the SMT solver really crashes and can't reason. So, but then you cannot also forget about these kind of constraints because they are very present in many of the circuits, and they form the bottleneck that makes the algebra and the polynomial arithmetic so difficult. And hence, coming from this graph, you can then try to get rid of those arms. So you exploit the graph structure, you see how things are connected to each other, you can simplify those arms, and you can kind of incorporate, you can use different methods to kind of separately look at the range analysis without feeding it into the Groebner basis engine, which would have to deal with these huge polynomials where it will get stuck. And then using this hybrid method, PICUS, which incorporates static analysis and these improvements on the solver, you can solve many more cases that were previously out of reach. Yeah, so unfortunately, I don't have too much time to go further into the details, but if you're interested, I'm very happy to talk about it offline. Okay, thank you. Yes.
So does this do better like an evaluation of like a read Solomon n log n?
I'm sorry?
Like, does the evaluation run in linear time? Or?
The evaluation of?
Like, well, most snarks work on like read Solomon encodings.
Yeah.
Usually the evaluation of that is n log n. Does this do any better?
No, this will be, like you will have a circuit which will turn into a polynomial equation, and then you will, from that polynomial equations, you will create a new system which will correspond to encoding the fact whether things are uniquely determined or not. And then you will have to check whether that is satisfiable or not, and that's kind of a very nonlinear problem, which is very hard to tackle in general.
So basically, they're solving two different issues. What you're talking about is the actual internals of the proving system, whereas this is trying to find bugs. And so the complexity is just significantly higher here, where you still have an undecidable problem rather than something that can run in logarithmic time.
No, that's awesome.
Thank you. Yes.
Yeah, thanks for the talk. I was wondering if you tried, specifically for CVC5 with finite field theorem core and for the range constraints, to take them out and express them as Boolean formulas over the finite field. So because CVC5 allows that, and yeah,
Yeah. I mean, when I said you use a separate range analysis, we tried that, and we even tried using an integer solver to do that, and that's how you really get the speed up. Like you have to free the solver from all range constraints expressed in polynomial form. And just as you say, using it, expressing them as Boolean constraint is one way, and then you have like different approaches, like always these DPLL-based methods where you kind of and you combine the different theories, and that's kind of how you get the improvement. Exactly.
Okay. What was the improvement like in concrete terms?
So I mean, since this is still a work in progress, I did not really put a table with saying, okay, this was the timing before, this is afterwards. And there's always this problem when you create benchmarks, are they representative or not? But what we did is we took a lot of benchmarks, lots of circuits that kind of we encountered during audits, and we fed them first into PyCus, which was just using a SMT solver that has finite field support together with static analysis. And it resolved many cases, but then there were like, among those benchmarks, there were like around 30 of them which it could not handle. And then with this additional approach, you could, out of those 30 that were out of reach before, you could maybe resolve half of them or 2/3 of them. And resolve means you get an answer within 5 seconds or so.
Okay. Just one last question. What did you do about circuits such as hash functions? Because, for example, when we tried to put the whole circuit, it just crashes. Memory is not enough. Did you separate it into much smaller chunks by hand?
That's a good point, very good point. I mean, for hash functions, what you do have to do is you have to, they are very modular. You'll have different parts that kind of feed each other, right? And if you look at them all at once, that will cause a problem because it will be too huge of a circuit to deal with. But like you have different parts that feed each other, and to conclude that everything is deterministic, you could just check that each of the components is deterministic, right? I mean, if you have deterministic input at each step, then the final output will also be deterministic. And once you do that modular approach where you chop it up into smaller pieces, you could also handle lots of those hash function computation circuits that check hash function computations. But their modularity was really a key point, as you say.
Yeah, thank you for the talk.
For pure static analysis stuff, how one size fits all is it? So are you kind of just adding to the list of those patterns that you talked about, or for a specific thing you're going to run it on, are you also kind of taking into account the shape of the specific code?
So basically we've got a bunch of generic patterns, so you don't have to take into account the structure of the actual code base, because we have, like Daniel was showing, we have a method of encoding that into a more easily understandable form, which was this graph. And so for that reason, it doesn't matter what the shape of that graph is, which is what you'll end up getting from the code base itself. Instead, each of the patterns that we have is generic, and it can conceptually work over any graph that's provided to it.
I guess what I mean more is like the is0 example that you guys gave, like the specific kind of pieces that are specific to a specific, I use the word specific a lot there, that are specific to a single use case you're looking at. Are you having to do a lot of kind of, I guess, hybrid approach of human and static analysis?
Yeah, so with static analysis, you're going to get a lot of we try to trim down the number of false positives. So like Daniel was showing, if you have kind of a naive method of expressing this divide by zero, you're going to get a lot of false positives because it will just identify every division. And so at that point, it's a matter of refining your method of performing detection in order to get more and more precise results. But when you talk about having like a human in the loop, typically the way that works is the static analyzer will, and unfortunately we didn't have time, but we have a lot of videos that show like how this will work in practice and show you what the results look like, where it will essentially give you a list of things that we detected, and then it's up to the human to go and look through them and say, this is a false positive, this is a true positive, and stuff like that. So the static analyzer itself isn't going to have a human in the loop necessarily, but the human does need to go and check and see whether something reported was a false positive or not. And then, we're obviously working on reducing the number of false positives as much as we can.
And the way you prove on that is not so much looking at the structure of the particular code, but adding more information about like the code as a concept. Like if we only look at the graph, then we have those issues, but if we look at the values at the same time, then we can decide if an edge is a problem or not. So you need to add more information.
I just wanted to check my understanding. Are you going from the R1CS constraint to the satisfiability, or are you going from the arithmetic circuit to satisfiability?
It doesn't matter too much, in fact, because this will be quite agnostic to how you express things. I mean, in the end, you want to express everything in terms of polynomial equations. So you could do that from R1CS directly, or even if it comes from another AIR, you would still be able to do that. I mean, this is kind of the work on the solver side is just to say, I have a polynomial equation that comes from a ZK application, which will have a very particular structure. And how would I resolve it? But I mean, you start already at the polynomial equations.
So in practice, we start with R1CS. It doesn't matter if, like Alp was saying, if you start with R1CS Plonk, or like a Plonk table, or if you start with the actual circuit itself, as long as you are able to perform that encoding, everything will be fine. And so we focus on the actual intermediate representation for this particular work, like R1CS and like the Plonkish tables.
Because I'm imagining going from the arithmetic circuit to SAT would be a lot easier. The reduction is like straightforward. So I'm wondering if you do that, if you will save yourself a lot of maybe challenges that you would face when you go from something so unsatisfiability like R1CS equations. If you go from the arithmetic circuit directly to the SAT solver, I'm just wondering if that would make things easier in terms of like some of the challenges that you
From what
mentioned.
we've seen, not really, just because in a lot of cases there are restrictions on how you can, express constraints in your arithmetic circuit anyway, and so it doesn't really buy you a whole lot in order to go from there to actual SMT. In some languages that are coming out now, you might get some improvement where someone can express their computation more naturally because they don't actually separate the computation from the constraints. So this would be your languages like, let me see, ArcWorks is a very good example of that, where it kind of has this relationship where it knows how to translate any arbitrary computation as long as it's within a certain form to constraints. And so you can possibly get better results by going from there to your actual encoding. But in a lot of the languages that we've seen, going from your arithmetic circuit to your constraints does not provide a whole lot of benefit, just because they're so simple.
May I ask you something? Yeah, well, because all these ZK proofs, they are mainly based on these constraint systems, but I wonder if these approaches can also be used for some other frameworks, for example, multi-party computation frameworks, because I imagine that these, for example, the divide by zero or underflow or overflow, these errors might be quite common. And I wonder if we can apply these techniques to multi-party computation, which is slightly different because we don't have all those constraints. So it's the representation in the polynomial form is different, but yeah.
Yeah, so multi-party computation is something that we want to get to at some point, but
Okay.
yes, conceptually multi-party computation can have similar bugs to what we're seeing here. And so That's something that is kind of on our roadmap to start exploring and develop some similar tools and techniques, which I imagine will look fairly similar to what we have here, or somewhat similar. Like if you look at them from, way kind of far back, then they will probably look fairly similar. Yeah.
Yeah. Okay. Cool.
And also to add a little bit of that, most of our workflow sometimes just like we reduce both the program, the readiness and the constraints into another program in which they will apply normal static analysis. We follow a similar procedure on those, it should be more or less the same.
Hi, thanks for the talk. Do you plan on providing support for other languages as well?
Yeah, so we're working on support for other languages. So CirCon was our first one, just because things were just so simple with CirCon because the DSL is dead simple. We're working on adding support for Halo 2, ArcWorks, Flunky 2, languages like that as well. There are other languages that we might be able to support as well that basically take away the effort of expressing the constraints, like let's say O1JS, but most likely because the backend is going to deal with encoding things as constraints, tools such as this are not going to be as necessary. And so we are working on expanding the set, and in some cases it's easy, like with the SMT approach that we were talking about now. It's just a matter of encoding your table as constraints, which is not very difficult. For other techniques, such as the one that Daniel was talking about, the static analysis, we have to kind of understand both the constraints and the computation. It can get more difficult to understand in some DSLs because, like if you're talking about Halo 2, you have to understand the arbitrary rest, which gets fairly difficult. And so instead, for languages like that, you kind of have to let go of the computation side of things, which is unfortunate because it means that there are some things that you can't detect, and instead focus primarily on the constraints. And so we're working on those trade-offs for other languages as well.
Where does Noir fall into this?
Right. Noir is something that we haven't spent a whole lot of time looking at this point. We, basically the way that we've decided which languages to support are based off of where we've been getting audits. And so we imagine that we will also start looking into other frameworks like Noir, particularly because it's got a very nice representation that a lot of things can count down to, but we haven't started looking into Noir yet.
Thank you.
Okay.
Thank you.
Thank you.